Right now, as you're watching this video, your device is performing what should be an impossible task. It's receiving thousands of tiny packets of data that have each taken completely different routes across the planet, bouncing through dozens of routers, crossing continents, and somehow reassembling themselves into this exact frame you're seeing. Every time you stream Netflix, send a text, or load a web page, you're conducting a real-time experiment in distributed chaos theory. And the fact that it works at all, that's not engineering, that's a miracle wrapped in mathematics. I'm Marco, and I've spent 20 years building the infrastructure that keeps your cat videos flowing. Today, we're going to explore why the internet is essentially a controlled explosion of chaos, and why that's exactly how it needs to be. Let's start with what you think happens when you click a link. Most people imagine something like this. Your computer sends a request into the internet cloud, and boom, web page appears. Clean, simple, predictable. But here's the reality. That innocent click just triggered a cascade of events that would make a butterfly effect theorist weep. Your request doesn't travel in a nice, neat line. Instead, it gets chopped up into hundreds of little packets, each one stamped with your destination address like postcards scattered to the wind. These packets don't all take the same route. Packet number 1 might go through New York, London, and Frankfurt. Packet number 2 could route through Los Angeles, Tokyo, and Mumbai. Packet number 3 might take a completely different path that didn't even exist when packet number 1 started its journey. Imagine if the Postal Service worked this way. You write a letter, but instead of sending it as one piece, they tear it into 200 fragments, put each fragment in a separate envelope, and then mail them all using different routes. Some go by truck, some by plane, some by carrier pigeon. They arrive at different times in random order, and your recipient has to piece them back together to read your message. That would be insane for mail delivery. For the internet, it's Tuesday. To understand why this chaos is actually genius, we need to go back to how communication networks used to work. The old telephone system was based on circuit switching. When you made a call, the network would establish a dedicated connection from your phone to the destination. Think of it like reserving a specific lane on every highway between you and your destination. This worked great for phone calls, but it's terrible for data. Imagine if every time you wanted to load a web page, the internet had to reserve a dedicated path just for you and keep that entire path locked up until you were done browsing. The whole system would collapse under the weight of everyone trying to watch TikTok simultaneously. So instead, we use packet switching, the chaos approach. Your data gets broken into packets, and each packet is like an independent agent with its own mission. Get to this destination address by whatever means necessary. No reserved paths, no guaranteed routes, just pure emergent behavior. In reality, the modern internet pretty much works on optimized routes to improve performance. Voice over IP even requires consistent network address translation in most cases. And in my experience, SSL connections were sensitive to route changes. I haven't experienced it recently, but felt I should throw that in for historical reference. This is remarkably similar to how ant colonies work. Individual ants don't have a master plan, but collectively they create incredibly efficient foraging patterns. Similarly, individual packets don't know about the global network state, but collectively they create a resilient, self-organizing system. Each packet carries just enough information to be independent. Source address, destination address, sequence number, error checking, and most importantly, route information. Think of it like a GPS that only knows the destination, not the route. Every intersection, router makes a local decision. Based on what I know right now, which direction should this packet go? No central coordination, no global optimization, just local decisions creating global behavior. Now here's where it gets really wild. Those routers making local decisions, they're not just guessing, they're running algorithms that are constantly gossiping with their neighbors, sharing information about network conditions, and updating their routing tables in real time. The most common protocol is called BGP, Border Gateway Protocol. I like to think of BGP as the internet's gossip network. Every router is constantly chatting with its neighbors. Hey, I can reach these destinations in 5 hops. Oh, really? I can reach them in 3 hops. Actually, that path just went down. Try this other way. This creates what network engineers call convergence. The network gradually learns about changes and adapts. But here's the kicker. Convergence isn't instantaneous. It takes time for gossip to spread, which means the network is always slightly out of sync with reality. It's like Heisenberg's uncertainty principle for networks. You can either know exactly where all the traffic is, or exactly where it's going, but never both simultaneously. The network is always operating on slightly outdated information, making decisions based on what it thinks is true. Let me give you a concrete example. Remember when Facebook went down in 2021? It wasn't because their servers exploded. They accidentally withdrew their own BGP routes, essentially telling the internet, "We don't exist anymore." The internet believed them and stopped sending traffic to Facebook. Even Facebook's own engineers couldn't access their internal systems to fix the problem because the internet had forgotten how to reach Facebook. This is chaos theory in action. A tiny configuration change created a global outage. The internet's distributed nature, which usually makes it resilient, became the very thing that amplified the problem. But packet routing is just one layer of chaos. The internet is actually 7 layers of controlled chaos stacked on top of each other, each one adding its own flavor of unpredictability. At the physical layer, we're dealing with electrical signals, fiber optic pulses, and radio waves. This is where physics meets networking, and physics doesn't care about your deadline. Signals degrade, cables break, interference happens. Every bit traveling across the internet has to survive this gauntlet of physical reality. The data link layer adds another layer of chaos. Ethernet frames collision detect their way across local networks. Wi-Fi packets politely wait for their turn to speak, unless they don't, in which case they collide and have to try again. It's like a room full of people all trying to have conversations simultaneously. The network layer is where our packet routing chaos lives. IP addresses, subnet masks, routing tables, all constantly changing, all making local decisions without global coordination. The transport layer adds flow control. TCP, the reliable protocol, is like a paranoid parent constantly asking, "Did you get that? How about that? Are you sure you got that?" UDP, the unreliable protocol, is like throwing messages in bottles into the ocean and hoping for the best. And the upper layers, that's where applications live, each one adding its own interpretation of what working means. HTTP redirects, DNS lookups, SSL handshakes, more opportunities for chaos at every level. When you load a single web page, here's what actually happens in the chaos. There is a DNS lookup. What's the IP address for this domain? Then a TCP connection, a 3-way handshake across the internet, followed by an HTTP request and response. Repeat until all the page files are loaded. Each of these steps involves packets taking different routes, routers making independent decisions, and protocols trying to coordinate without central control. It's amazing that anything works at all. So why does this chaotic system actually work better than a centrally planned one? The answer lies in what chaos theorists call emergent properties, behaviors that arise from the interactions of simple rules, not from top-down control. In a centralized system, there's a single point of failure. If the central controller goes down, the entire network fails. But in a chaotic system, failure is localized. When a router goes down, the network routes around it. When a cable gets cut, traffic finds another path. The chaos isn't a bug, it's a feature. This resilience isn't theoretical. During natural disasters, wars, or infrastructure failures, the internet literally routes around damage. Packets find paths that human network engineers might never have thought of. The system's ability to adapt and self-heal emerges from the chaos, not despite it. There's also an economic reason chaos works better. Coordination is expensive. If every router had to check with a central authority before making a routing decision, the latency would be unbearable. Instead, local decisions based on local information create a system that scales to billions of devices. Think of it like evolution. Random mutations are constantly occurring. Most are neutral or slightly harmful, but occasionally one is beneficial. The network naturally selects for paths that work better. Lower latency, higher throughput, more reliability. No central planner needed. From a mathematical perspective, the internet exhibits properties of what chaos theorists call a strange attractor. Despite the apparent randomness, the system has underlying patterns and stability. Traffic flows find equilibrium points, routing tables converge to stable states, and the whole system exhibits predictable behavior at scale, even though individual components are chaotic. But here's the thing that really makes the internet chaotic. Humans are involved. Every day, thousands of network engineers around the world are making changes, adding new routes, updating configurations, fixing problems. Each change ripples through the system in unpredictable ways. I've seen tiny configuration changes take down entire regions of the internet. I've also seen networks mysteriously start working better after changes that should have made them worse. The interaction between human decision-making and automated systems creates a level of chaos that no model can fully predict. And the system keeps growing. Every day, new devices connect, new networks peer with each other, new protocols get deployed. The internet is like a city that's constantly under construction, with traffic flowing around the construction zones in real time. This is where technical debt comes in. Every quick fix, every temporary solution, every "we'll clean this up later" decision adds to the system's complexity. The internet is held together by decades of accumulated technical debt, and somehow it keeps working. So the next time you're streaming Netflix, remember what's actually happening. Your video is being torn apart into thousands of pieces, scattered across the globe through a chaotic system of autonomous agents making local decisions based on incomplete information, and then reassembled in perfect order on your screen. The internet works because of chaos, not despite it. The same principles that make weather unpredictable make the internet resilient. The same mathematical concepts that describe turbulence in fluids describe traffic flow in networks. And as we move toward even more distributed systems, edge computing, IoT, mesh networks, we're not reducing the chaos. We're embracing it. We're building systems that are even more distributed, even more autonomous, even more chaotic. The internet is humanity's greatest achievement in controlled chaos. It's a system that works precisely because it's not designed to work. It's resilient because it's fragile. It's predictable because it's random. If you found this deep dive into internet chaos theory fascinating, subscribe for more infrastructure deep dives. And remember, every time you click that subscribe button, you're participating in a beautiful dance of distributed chaos. Your click will travel through dozens of routers, cross multiple continents, and somehow, miraculously, increment a counter in a database somewhere. The internet, where chaos theory meets daily life, and somehow it all just works.